Noga, Alon from Tel-Aviv University and the Institute for Advanced Study, who will speak 48 minutes on strong and weak epsilon nets. We're going to take Noga out for dinner at Evelyn's restaurant in downtown New Brunswick at 6:45. Everybody is welcome to join us, but please let me know immediately after the talk.
Okay, thank you. And thanks for coming. So it's a pleasure to be here. And I speak about strong and weak epsilon nets. And please don't hesitate to stop me and ask questions in the middle whenever something does not make sense. Maybe the sort of experimental part of this lecture will be near the end, but we'll see. Okay, so I want to define everything. I don't want to assume anything. And the first definition is the definition of a range space. So the range space, or a hypergraph, if you prefer this terminology, is an ordered pair, and it has a set X, which could be finite or infinite, and this will be a set of points or objects. And then it has a set script F that you see here. I'm kind of using the laser pointer looks a little bit degenerate here, but so this is a set of a family of subsets of X, and these are called ranges or edges. Think about the hypergraph terminology. And an important notion is to say when a set of points, a subset of the set of points, when it is what is called shattered. So a set of points, a subset A of X is shattered if for every subset of it, B, you can get B exactly as the intersection of A with one of your ranges, right? So if this is a finite set of K elements, for all the 2 to the K possibilities of choosing some subset of it, there is some range so that if you intersect it with A, you get exactly this subset. So this is a shattered set. And we would be interested in the maximum or supremum size of a shattered set. So this is called the VC or Vapnik-Chervonenkis dimension of this range space. So this will be, and we'll soon see several examples. So this, the VC dimension of this range space, XF, is the maximum cardinality of a subset that you can separate by intersecting with ranges in all possible ways. So I said maximum, formally it's supremum because maybe there are sets of all possible sizes, and then this thing is infinite. Maybe in fact there is even an infinite set that is shattered, and then also it's infinite. But the interesting case usually will be when it's finite. So let's see some examples and just to practice the definition. A simple example is that the set of points, our set X, is the set of all points in the plane. And the set of ranges are all the half planes, right? So we take some line, and actually there is a picture here. We can take a line and we can just take all the points, say, above this line. These are the ranges. And I claim that the VC dimension of this is 3, because here you see 3 points, so just 3 points in general positions that are not on a line. Then you see that there exists, of course, a half plane containing all 3, and for every pair of them there exists a half plane containing exactly this pair, and for every 1 point there exists a half plane containing this 1 point, and for 0 points also there is a half plane not containing any point. And on the other hand, if we have 4 points, so it depends how they look, but for example 4 points in convex position, so if they look like this, then we cannot separate this pair from this pair, right? Any half plane that we cannot have a line that will separate this pair and this pair, actually, because the convex halves of them intersect. And the same if we have a triangle and a point in the middle. So the VC dimension of this is exactly 3. Here is an even simpler example, so still just to make sure we understand the definition. So if the set of our points is all the points, again, in the plane, and now the set of ranges is just the set of all lines, then the VC dimension is 2. If we have 2 points, then there is a line containing both, there is a line containing this one, a line containing this one, a line not containing anyone. And if you have 3 points, well, if all 3 are on a line, then no line can contain 2 of them without containing the third. And if not all 3 are on a line, then no line can contain all 3 of them. Right? So the VC dimension in this case is 2. This is more or less the simplest example, and it will come later again. Here are some maybe more general, slightly more interesting examples. So first, the obvious extension of the first one. The set of points now is the set of all points in the d-dimensional Euclidean space. And the set of ranges is again half spaces. So we take a hyperplane and we take all points above this hyperplane. Then the claim is that the VC dimension here is d plus 1. If we take d plus 1 affinely independent points, so they form the vertices of simplex, like we saw the triangle before, we can separate them in all possible ways. So for example, if you take the origin and all the unit vectors, you will be able to separate them in all possible ways. And if you have d plus 2 points, then there is a very simple theorem of Radon that says that it's basically linear algebra, that if you have d plus 2 points in Rd, then you can always separate the set into 2 disjoint sets so that the convex hulls intersect. And if the convex hulls intersect, we will not be able to separate one from another by a hyperplane, because then the convex hulls could not intersect. Okay, so that's why it is not. It is smaller than d plus 2, and it's at least d plus 1. So it is d plus 1. Here is a slightly more sophisticated example. So we fix some dimension, 17, I don't know, and we take all the semi-algebraic sets of constant complexity S. So what does this mean? It means, so these are intersections of polynomial equalities and inequalities in the variables. And the complexity is somehow, let's say, the total degree of all these polynomials together. So I don't want any degree will be very high. And then one can use some known results from real algebraic geometry, specifically of Miller and Tom or of Warren, to bound the VC dimension of this, and it will be some bound that is a function, usually a nice function of D and S. Okay, so for example, an example of such a thing could be maybe balls, let's say, in the 17-dimensional Euclidean space, because what is the set of points inside a sphere is a set of points in a ball. So we just have 18 parameters, right? So this, the parameters are like the coordinates of the center of the ball and the radius of it. And then we have one polynomial inequality. That's a sum of xi minus ai square is at most r squared. So this is indeed some semi-algebraic set. It's a polynomial inequality of degree 2. And because of this, we know that the VC dimension will not be too big. If you have very many points in R17, then there will be some sets that you cannot separate from its complement by a ball. Okay, so this is, and of course, some more complicated semi-algebraic sets like this. So we have many examples, and hopefully we understand the definitions. And here is so the title was talking about epsilon net, strong and weak. So here is the definition of a strong epsilon net. So we have a range space. Let's call it the objects, they are points. So this will be, and you can think about one of the examples before if you want, or just an abstract range space, say. And inside it, we take a finite set of points, A. Okay? And we'll call a subset of A an epsilon, a strong epsilon net. So usually it's called, this is the usual notion of epsilon net. So sometimes we omit the word strong. So this will be called a strong epsilon net for A if whenever you have a range that contains a big fraction, at least an epsilon fraction of the total number of points, then it contains at least one point of x. Okay? So for example, here you see, well, you almost see, this was the last 6, 8, yeah. So you see here a set of 8 points. I mean, you see half of the bottom one of them, but you see all the others. And suppose that our epsilon is 3/8, and the ranges are half-plane ranges. So what we want is to pick some subset of this set of points so that every half-plane that contains at least 3 of the points, because this is 3/8 fraction of this 8, will contain at least one point of the subset x. And here is this subset, so we make the points bigger. So this is x. And you see that whenever, I mean, these are points in convex position, so it's easy to check. What you see here is an example of some half-plane, all the points below this line, to the right side of this line. So this contains 3 points, at least 3 points. In this case, exactly 3 points of our set of points. And indeed, it contains at least 1 point of the chosen points. And this will be the case whenever we take any half-plane that contains at least 3 of the points. Okay? So this is an epsilon net, and somehow this, okay, so maybe I'll tell you another related notion. So this is something similar. This is called an epsilon approximation. So that's also, we have a finite set of points in a range space, and a subset x of it is now called an epsilon approximation, so it's something a bit stronger than epsilon net. If not only it captures a point from each big range, but actually it approximates the sizes in the following sense. Whenever we take a range f, then you see we can compare two quantities. So we can look at the fraction of the number of points of A that the range contains. This is this ratio. And we can look at the fraction of the number of points of x, the small set that is supposed to be an approximation that a range contains. And the difference between them in absolute value should be smaller than epsilon. So they should be about the same. So in some sense, this x that you can think about it as a sample, it represents well all the ranges. And you see that an epsilon approximation is necessarily also an epsilon net, because what is it in epsilon net? If A intersection F is bigger than epsilon A, then this quantity is bigger than epsilon. So this quantity should be non-zero. Otherwise, the difference will be too big, right? But the converse is obviously is not true. So an epsilon approximation is something that is a bit stronger. But in a way, they are similar. And here is some basic theorem of Hausler and Welzel. From the 80s, it really follows the original proof of Vapnik and Chervonetkis. It's a very nice proof. So it says the following, that if we have some finite set A in a range space of VC dimension D, think about D as small, maybe one of the examples we had before, then it contains an epsilon net, so some subset of it, which will be an epsilon net, and its size is very small. So how small? Some absolute constant times d over epsilon times log of 1 over epsilon. The important thing here at this point is maybe that it's independent of the size of the set A. So for example, I give you a huge set of points, billions and billions of points in the plane, okay? Then and we fix epsilon to be, say, 1%. Then we will be able to choose some constantly many points, I don't know, 1,000 points, so that whenever we take a triangle in the plane, the set of triangles also has bounded VC dimension. It's not difficult to see. So whenever you take a triangle in the plane that contains at least 1% of these billions of points, it will contain at least one of our set of 1,000 points. And this 1,000 is independent of how many points we have to begin with, which is quite amazing, because actually the proof, so the proof is a probabilistic proof and elementary but clever, and it actually shows that a random set of appropriately many of these many points, a random subset of the set of points that we have, will have the desired property with high probability. And somehow, if you try to do the standard things that appear in probabilistic proofs, you will get dependence on the size of the big set. Maybe logarithmic dependence, but some dependence. So the nice thing here is that this function is completely independent of the total number of points. It's always small, and we'll see why this is useful. So again, I stressed here that indeed the size of this set is independent of that of A. And maybe another remark that could be interesting is that if the VC dimension is infinite, then, so whenever the VC dimension is finite, then you see for every epsilon, even if you give me a very, very big set, I can find a very small epsilon net. And you see if the VC dimension is infinite, then for every size, there is a set of this size which is shattered. That was the definition. Namely, all subsets of it are obtained by intersections with ranges. So if you'd want an epsilon net for such a set, you would have to pick almost all its elements. You'd have to pick 1 minus epsilon times A elements, because even if you omitted just epsilon A points of this set, then there is some range that contains exactly these points. And therefore, this range should contain something from the epsilon net. Right? So it means that there is some dichotomy here. So either the VC dimension is big, and then for some sets, you need huge epsilon nets, namely you need basically to take all the set, or the VC dimension is bounded by something, and then for very big sets, you need very small epsilon nets. So they are okay. Now the same thing actually holds for epsilon approximation. This was an older theorem of Wicks-Chervonenkis. The proof is similar, and it says again that if A is a finite set in a range space of VC dimension D, then it contains an approximation of size, again, 10 maybe times D over epsilon squared, log of 1 over epsilon. So again, it's kind of independent of the size of the big set. Let's see, maybe I mentioned why this is useful. So I wrote here that those notions of epsilon net and epsilon approximation, they play a crucial role in discrete and combinatorial geometry, also in learning theory, also in combinatorics, in statistics. So they appear a lot, and I just want to show, if you haven't seen any of these notions before, let me show you a very simple example why this can be useful. So this will be like a computational example. So suppose we fix epsilon. So think about epsilon as 1 over 100, 1%. And suppose we have a finite set of points in the plane. But again, it could be a huge set of points. Right? So very many points in the plane. And now I want to take an epsilon approximation. So which example? Yeah, so we took here 4 triangles. So we look at the range space of triangles in the plane. This has finite VC dimension, maybe 7 or something like this. So because of this result of Wapnick and Chervonenkis, there is a constant size epsilon approximation for this epsilon equals 1%. So what does this mean? It means that I can pick, and in fact, I can do it efficiently. I just have to pick randomly some of my points. So I can pick a constant number of points, maybe 1,000 points. Just remember these points and forget all the rest. So these are 1,000 points. Now I remember only them. So you see that this is a very small data structure. It is of constant size. I just have to remember these 1,000 points. And now you give me some triangle, any triangle. So I just have to count how many of my 1,000 points lie inside this triangle. And if there will be about 1/3 of them that lie inside the triangle, then I will know, because this is an epsilon approximation, I will know that up to 1% error, the same holds for the big set. So I have some very small amount of information that I have to maintain, and then I have a constant time procedure that enables me to approximate how many points I have inside each triangle. Okay, and the same for any for anything of bounded VC dimension. Because of this, this is useful. So it appears this would be one implication. Any questions, wonders? Okay, it's clear. So if, but again, don't hesitate to stop me if something is not clear, and if it's too slow, then you can also tell me that. Right. So, all right. So, so there is an example. Actually, the first example is by Komruk, Schbach, and Woginger. There are other examples as well. That there are abstract range spaces of VC dimension very small, 2. So in VC dimension 1 is not too interesting. It's completely understood how they look, and nothing very interesting is happening. But with dimension 2, already some interesting things can happen, at least in abstract spaces, maybe not geometric ones. And there the epsilon nets for some sets of points are indeed of size 1 over epsilon log of 1 over epsilon. So really that estimate that we had before in the theorem of Hausler and Feldsel is tight for some examples. And people wondered if in geometric situations, because many of the applications of these are in discrete and computational geometry, if in geometric situations we need this log of 1 over epsilon term. So somehow the 1 over epsilon, we basically need it in all interesting examples. And the question is, do we need this extra log factor? And so specifically the problem and the way it's formulated here, but this is the way they formulated it, Matuszek, Seidel, and Feldsel, some 20 years ago. So maybe you can be more formal about it by defining what it means, natural geometric scenarios. But let's just say that the belief was that in every natural geometric scenario, like the examples we saw at the beginning, of constant VC dimension, we don't need this extra log factor. And people somehow worked on this. So, so there are several, so I listed here some papers, there are more, and they all deal with some special cases. And in all these special cases, indeed, we don't need this log of 1 over epsilon. Namely, these are indeed very, very small epsilon nets. So I wrote here a few point objects. So if my objects are points in 2 dimensions or in 3 dimensions, and the ranges are half spaces. Or if the objects are points and the ranges are disks or pseudo-disks, and there are some dual examples. So there are several examples where it is known that we don't need this log of 1 over epsilon. And each of these cases requires some clever ideas. So somehow they seem to be tailored specifically for this specific example. Now it may look a little bit that why do we care so much about this log of 1 over epsilon? So again, just stating what, so in all these papers, they all conclude by saying that the prevailing conjecture is that indeed in all geometric situations, you don't need this log of 1 over epsilon term. Namely, there is this very small epsilon net. And I should say that in some geometric applications, we kind of care about this logarithmic term. And let me just say that if we look at some geometric instances of set cover problem, so you can think about, I don't know, you have again points in the plane, you have collection of triangles, let's say, and you want to find the smallest possible minimum, the minimum possible number of points that intersects all the triangles. So this in general is a difficult problem to solve it exactly, but you can solve the linear programming, the relaxation of it, solve it fractionally, and then somehow the ratio between the fractional solution and the integer solution has something to do with this extra term of log of 1 over epsilon. So this should not necessarily make too much sense, but it's just to say that there are some algorithmic motivation to try to get rid of this log of 1 over epsilon. Okay. And indeed, one thing I want to describe is that indeed it turns out that this is not linear. So it is not true that in all geometric situations there are epsilon nets of size 1 over epsilon. In fact, more or less in the simplest geometric situation you can think about of VC dimension 2, then we need some extra term. So this will be one result that is really very simple. So I try, like in the last maybe a third of the lecture, to describe the proof. So there is a set of points for small epsilon. There is a set of points in the plane, so that if you want to take epsilon nets with respect to the ranges of lines, so the range space here is very simple. The points are just points in the plane. The ranges are lines. Okay, and the claim is that there you need to take a little bit more than constant over epsilon number of points in the epsilon nets. Namely, so unfortunately what the proof gives is that it's just a little bit more. The number of points you will have to take is 1 over epsilon times some function, I wrote it here, omega of 1 over epsilon, or w, where this w will be some version of the inverse Zuckerman function. So this is what follows from this construction. So, so again, it's not crucial to know what exactly is the definition of this function. It's a version of inverse Zuckerman function. But what we care about is that it's a function that goes to infinity when 1 over epsilon goes to infinity, but it goes very, very slowly.
Slower than log, 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 right?
And slower than, I mean, much, much slower. I mean, so it's not even, right. So it's slower than anything, right? So still the value of this function of the number of atoms in the universe is maybe 4 or 3, but it goes to infinity. So still, however, soon after that, yeah, there are some extensions, but let's not worry about that. And soon after that, there was a better quantitative estimate. So that's another theorem by Pach and Tardosh. And what they say is that if we look at another, maybe slightly more complicated range space, so, but still pretty simple. So look at the first one. The objects are points in the plane, and the ranges are axis parallel rectangles. Okay? Then this, for some configurations of points in the plane, requires epsilon nets of size 1 over epsilon log log of 1 over epsilon. That's already somewhat big. And if we allow some more complicated range space, which is dual, so I don't want to even describe it, but it's something, then it will still be geometric. It will have maybe VC dimension 4 or something, and it will require epsilon nets of size 1 over epsilon log of 1 over epsilon. So really, this log of 1 over epsilon in general is needed. However, the first construction, the one that gives this inverse Zuckerman, has some advantage. And the advantage is that it gives the lower bound even for what is called weak epsilon nets. And this gives me the opportunity to tell you about weak epsilon nets and to say something about why they are useful. And then I'll try to describe the construction. So yeah, everything will be simple. So what is a weak epsilon net? It's almost the same as an epsilon net. So again, we have a finite set of points in some range space. This will be A. And now a set Y of points, which is not necessarily a subset of A. That will be the main difference between strong and weak epsilon net. So just some set of points, some other set of points. It is a weak epsilon net for A with respect to the ranges of the space. If whenever a range contains an epsilon fraction of the number of points in A, then it contains at least one point of Y. So if you still remember it, it's exactly the definition of usual or strong epsilon net. The only difference is that now we don't assume that Y is a subset of A. It can be from outside A. It gives us more freedom. I think I even wrote it here specifically. Y is not necessarily a subset of A. And therefore, we sometimes could hope to get weak epsilon nets which are small, even when there are no small, strong epsilon nets. And in fact, there are quite a lot of interesting examples like these. And let me tell you one. So So this is the definition of weak epsilon nets for convex sets. Okay, let's say in Rg. Now you see, if you take the family as ranges all convex sets in the plane, this trivially has infinite VC dimension, because if you take points in convex position, for example, takes a set of all points on a circle, all the points on a circle, every subset of it, you just, so it's a subset of the circle, you just take the convex half of it, the intersection of